So we have definitions of linear dependence and linear independence. If you want to verify whether or not a list is linearly independent, you need to set up the equation where you take a generic linear combination of your list of vectors and set it equal to the zero vector, and then determine whether or not the scalars that you used in the linear combination have to equal zero. In the examples we saw, what we ended up doing was we set that equation up, which gave us a system of equations, and then we saw that whether or not the list was linearly independent hinged on whether or not we had free variables in the system. So this could be codified into a numerical test that tells us whether or not a list of vectors is linearly independent. And this is great because this is how we can ask a computer whether or not a list of vectors is linearly independent. So here's the precise statement. The columns of a matrix A are linearly independent if and only if the nullity of A equals 0. Think about why this makes sense. When you set up your system of equations, what you end up doing mechanically, and what we saw in our examples, is that you end up putting the vectors you're interested in into the columns of a matrix, and then you want to check that there are no free variables in the system that matrix times x equals the zero vector. But the thing that controls whether or not you have free variables is the nullity. So independence means the nullity of that matrix is 0. Dependence means that the nullity of that matrix is bigger than 0. So here I have two generic examples to illustrate the concept. On the left here, we are starting with a matrix. This one's 4 by 3. So the idea is that I had 3 vectors in R4, and I'm curious whether or not those 3 vectors were linearly independent. So I put them into the columns of a matrix, and then I did the row reductions. What do we find here? We find that every column is a pivot column. Well, this means that the nullity is 0. There are no non-pivot columns. So the columns of the matrix I started with are linearly independent because the nullity of that matrix is 0. On the right-hand side over here, we have the opposite situation. Here, we were studying another list of 3 vectors in R4. We wanted to know whether or not that list of vectors is linearly independent. So we put them into the columns of a matrix. We did the row reductions. And what do we find here? We find that we get 2 pivots, but then we have a non-pivot column. Remember that non-pivot columns give you relationships between the columns of the original matrix. This one is telling us that the first column minus the second column minus the third column equals 0. This means that the columns of this matrix are linearly dependent. So what we're finding here is that this matrix has dependent columns because the nullity of this matrix is 1, which is bigger than 0. An equivalent way of thinking about this linear independence test is to say that having independent columns is the same thing as saying that the matrix you're studying has full column rank. Remember, full column rank means that the nullity is 0. So let's do an example here. Here I'm studying a list of 4 vectors in R3. And I want to know whether or not this list of 4 vectors is linearly independent. Well, I can apply the linear independence test. I put these 4 vectors into the columns of a matrix. And now what I want to know is whether or not this list of vectors is linearly independent, which is the same thing as asking whether or not the rank equals the number of columns. And normally, I might have to do some row reductions to figure this out. But if you think about the way this matrix looks, here we have 3 rows. If I have 3 rows, I'll never get a rank bigger than 3 because you can't have more than 1 pivot per row. So for this matrix, the rank can never be bigger than 3. It might be 1, it might be 2, it might even equal 3, but you'll never get a rank bigger than 3 if your matrix is 3 by 4. In particular, we'll never get rank 4, so this matrix can't have full column rank. So the conclusion here is that the list that I'm studying has to be linearly dependent because of the linear independence test. Here what we have is a specific situation where we didn't actually have to do row reductions because of the shape of this matrix. So that's pretty cool. There are now many consequences of the linear independence test. One of which says that the pivot columns of any matrix always form a linearly independent list. So here we have this giant example. So I'm not even going to bother to count the number of rows and the number of columns. This is a big matrix. But I did the row reductions on this matrix, and I got this reduced row echelon form. Well, what is this telling me? First of all, this is telling me that the matrix I'm studying has rank 1, 2, 3, 4, 5. And the pivot columns are the original first, second, fourth, sixth, and seventh columns. Well, this theorem is telling me that those columns of the original matrix are linearly independent. And this gives us a new interpretation of the rank of a matrix. The idea is that if you just study different columns of the matrix, some of those columns might be linearly independent as a list of vectors. Other groups of columns might be linearly dependent. The rank of that matrix is the maximum number of independent vectors among the columns. So the important thing here is that the pivot columns of a matrix always form a linearly independent list. And like the takeaway from all of this is that the non-pivot columns depend on the independent pivot columns. So here we have a 4x3 matrix, and I wanted to point out that the third column here is the sum of the previous two columns. So 1 plus 3 is 4, 9 plus 0 is 9, 4 plus 2 is 6, and 1 plus 6 is 7. The idea now says if you delete non-pivot columns, you're not changing the column space of that matrix, because you could always recover those non-pivot columns by taking linear combinations of the pivot columns. So in other words, the column space of my original matrix is the same thing as the column space of the matrix obtained by deleting the non-pivot column. So here I've tried to type this out so that like what I'm conveying is that if I delete this third column, I'm not changing the column space because that third column here depended on the previous two. I couldn't delete any more than that though, because the remaining two columns are the pivot columns, and if I delete a pivot column, I am potentially changing the column space. And the last thing I want to point out is that we have a nice geometric interpretation of this idea. So we have our first two columns, column 1 and column 2, and we know that column 1 plus column 2 is equal to the third column. So in our figure, we could represent the first two columns as arrows in space, and then the third column would look like this. Because to get from the beginning of column of this vector, which represents column 3, to the end, we're going through column 1 and then through column 2. So what we have here is sort of a diagram that illustrates the dependencies between these three columns. We can use the first and second columns to reach the third column. And this is sort of the idea behind independence and dependence. The first two columns here are linearly independent, but then we can use those two columns to reach the third column by adding them together here, and that illustrates how these three columns are dependent.